All right, so this is very strange. I got a text from the school fairly late last night saying, you know what, we don't have any power here and we don't know when it's coming back. And so they did cancel classes last night. So I thought it might be prudent to schedule this morning just in case they were still having issues. You never know with power. I mean, there was one year where a bunch of trees fell over because of the wind and there was no power for almost a week. So anyway, this is not the worst thing in the world because anybody who can't make it can still watch the recording. And then if you're on campus, you just don't have to walk over to the classroom. And if you're a commuter, it's even better because you don't have to drive to school. So,
I'm literally driving right now. I'm on like the I-84 already speeding.
uh-oh, are you
YOLO. No, I
okay?
saw the email and I was like already halfway there.
Oh,
It's
okay.
whatever.
All right. Well, I'll tell you what, if you miss anything, it'll be recorded. But I guess you're on your phone right now?
My car has like I have Zoom on CarPlay,
You do?
great
Oh,
feature. So like I can do
no
Zoom
kidding.
meetings in my car. It's great.
No kidding. You know, I have CarPlay too, but I really don't use it very much. I usually use it for directions. I guess there's a lot of things it can
It's
do.
great. Like you can do Zoom meetings on here, FaceTime, group
Uh-huh.
calls, like everything.
Oh,
So
okay.
like
Well,
Zoom
that's good to
literally
know.
like shows me like it literally like plays fine, like
Uh-huh.
normal Zoom meetings. So yeah.
Okay. All right. Well, that's good to know. But yes, but I'm going to put the recording on Brightspace and in my YouTube account just in case anyone misses anything. So, anyway, so where we left off was we didn't quite finish our review session for the second midterm. So we're very close though. So when we're done with this part, we'll go back and revisit where we left off with matrix algebra. Now, it's been a while um, since we looked at matrix algebra, but we're just going to go back and dive back into it. And you'll see that it's going to take a little practice. It's the kind of thing that it takes a lot of work to do it by hand, although usually matrix algebra problems are solved with computers. But we have to understand what's going on behind the scenes, especially because, like I've said before, if anyone is a math major, you're going to need this for when you start linear algebra, which um, is a very, very different discipline than calculus. And in fact, ironically enough, I just the other day I saw on Instagram somebody posted um, he was telling everybody how different linear algebra is from calculus. You wouldn't think that would make its way into YouTube or not YouTube, Instagram, but there it was. So there's something for everyone on Instagram, even math. So anyway, let's get back to this real fast. So we left off we did number 12. We didn't quite get to number 13. So what is this reference angle all about? Now, we do have a document in Brightspace somewhere that helps us with this. So let me go open it up. Let's see. Oh my God, I have so much stuff open. Either that or I'll just get it out of my own notes. That might be quicker. But with a reference angle, what you're essentially doing is looking for the shortest path back to the horizontal axis. So let's see. Huh. Well, I don't see it there, so let me go get it off of Brightspace. So if you remember when we were doing the trig content, that there were actually two documents that I put in the trigonometry section. So let me just get them both open just in case we need them. Um, so they were called the unit circle and the reference angles. So if you go into our class under chapter 4, you'll see them there. And of course, since you'll be doing the second midterm online, you can certainly feel free to use this as a reference. Here it is, reference angles and trig circle. So let me quickly open those up. Just as a quick reminder of what they're for and how they're going to help us with these questions. All right, here we are. Here's the reference angles. Then we're going to need the we might need the unit circle. Maybe we will, maybe we won't, but that's okay. So let me just get it open. So if you remember this, the purpose of this one is that you can quickly and easily look up the sine and the cosine of any of the angles that you see listed here. And if you notice, they're all listed as both degrees and in terms of radians, but just be aware that in each case, the x coordinate is the cosine and the y coordinate is the sine. Okay, so like right there, what that's telling me is that this cosine of 60 degrees or pi over 3 radians is 1/2, and the sine of that same angle is radical 3 over 2. But as far as the reference angles go, that depends on what quadrant we find ourselves in. And so let's take a look at the first question. So the first one is -120. So right off the bat, we have a negative angle. So it's probably, maybe it's not absolutely necessary, as long as you can identify where it's located. But remember, negative angles mean that you're moving clockwise. And each quadrant, if you recall, covers 90 degrees. So that means what I'm actually doing is moving through the fourth quadrant and then 30 degrees into the third quadrant, which means that I'm in the third quadrant. And as far as the reference angles are concerned, that's really all you need to know. But if you wanted to know what is the equivalent positive angle, which means we're going counterclockwise, the trick here is that the two of them have to add up in absolute terms to 360 degrees because they make a complete circle. So that means if you're moving the other direction, it'll be 90, 90, and 60. So -120 is the equivalent of positive 240. Anyway, so if you look at this chart that we have here, graph, that means we're in the third quadrant. If you notice, the reference angle is angle minus 180. So this one, I believe, is designed to make sure you understand that this is, you should be using the positive angle for this chart. You could, I suppose, try the -120, but I think you'll just get confused. So for using this chart, your best bet is probably to convert negative angles into positive angles so that you can apply the rule, which you can see in the third quadrant is angle minus 180. So again, the rule here is angle minus 180. And that in turn would be positive 240 minus 180, which is 60. Now, if you don't want to go through all those steps, the other way, like I said, the way to think about it is that you're looking for the shortest path to the horizontal axis. So if you're here, the quickest way to get back is to just move 60 degrees in this direction. And so that's what that's all about. It's 60 degrees to get back to the horizontal axis. Then for B, now this one, we also may want to simplify it for different reasons. 405 degrees means we've gone around the circle more than once. So you have to imagine with this one, you've gone around the entire circle once plus another 45 degrees. So 405 and 45 means the same thing. And how can you tell? Because if you subtract 360 from the 405, you'll wind up with 45 degrees. Once you're there, you're good as far as the reference angles go. In fact, within the first quadrant, the reference angle of any angle is the angle itself. Okay, so that means that here the reference angle in the first quadrant is the angle which is 45. So that's the easy quadrant. When you're in the first quadrant, it's a breeze to figure out the reference angle. All right. Oh, by the way, these handwritten notes, these take the place of what I would normally be writing on the board. I will be saving this and posting it onto Brightspace if you want to look at it. And then, of course, when we're done, I'll be posting the entire set of solutions that are completely typed up and that all the details are there so you can go through it and study it if you need to. So that way you'll have all the information you need when you start taking the second midterm, which is not due, by the way, until the 14th. All right, 760 now. We got the same situation. We've gone around the circle twice now because it's every time we go around the circle, it's 360 degrees. So that means 2 times around is 720, and therefore 760 minus 720 equals 40 degrees. So we went around twice. Let me tricky to draw this. Oh, sorry, I'm going the wrong way. Well, all right, that's not a terrible diagram, I guess. You just have to remember that you've gone around twice, which brings you back to the starting point, and then you've gone on another 40 degrees into the first quadrant, which means in the first quadrant, again, the reference angle is just the angle itself. So it's just 40. All right. And then finally for D, we have negative 180. This is an interesting one. Again, the negative indicates that we are moving in a clockwise direction. That means going this way until we find ourselves back on that horizontal axis. And, if you want to do the positive version of this angle, you can see you're just doing the same thing, except it's positive. Either way, we find ourselves right on the the horizontal axis. So in the third quadrant, we're actually right on the border between the second and the third. So since we're right on the horizontal axis, the reference angle is actually just going to be 0. Because we're already on the axis. Okay. So we're there. We're where we need to be. If you look at these, you'll notice that since we're on the border between the second and the third quadrants, either one of these would do the job. In other words, if you notice in the second quadrant, the reference angle is 180 minus angle, which would be 0. And in the third quadrant, the rule is angle minus 180, which is again 0. So any way you look at it, in this case, the answer is 0. Now, I do want to point out that all of this applies equally to radians. The difference there is that we have to convert the degrees into radians. Okay, now how do you do that? Let's go back to our chart for a second. And remember that very famous relationship I've been harping on all semester. Pi radians is 180 degrees. So that means I can change this to pi, and 2 pi. And I'm all set with the understanding that the angle is measured in radians. Okay, so we don't really need 2 separate charts for this. If you're using radians, just change 180 degrees is 2 pi, 2 pi is 360. Okay, so that being the case, let's see what we've got here. Right. So the first one is 3 pi. Now, just like with degrees, the entire circle is 2 pi, which is 360. So if you have an angle which is larger than that, that means you've gone around the circle once and then a little further than that. So this one means that we went all the way around 2 pi, and then we went continued all the way over here to the horizontal axis. Each quadrant, remember, is equal to pi over 2. So if you were to draw out a little diagram showing that, it would look like this. Okay, so in other words, this means 0. If you want degrees, it would look like this. All right, so based on that, you can see from all these examples where we'll wind up given the number of radians that we've moved around the circle. Now, with B, 4/3 pi, where would that put us? Now, if it really confuses you to think about radians, what you can do is just simply go ahead and convert it into degrees. And in this case, you're going to have 240 degrees. Okay, which means you're basically going through 2 quadrants and 60 degrees in the third quadrant. Or you can think of this as pi over 2 plus another pi over 2. And 60 degrees is pi over 3. So that means you're going to have, how far have you gone? If you convert these into sixths, oh wait, what did I do? Sorry. This one becomes 4/6. So that's where this has come from. Now, with our chart, you can see that since we're in the third quadrant, the reference angle is either angle minus 180 or angle minus pi. So here the reference angle could be thought of as so that's 4/3 pi minus pi, which is pi over 3, which again, remember, is 60 degrees. Okay. So if you're doing this in a MindTap assignment, I don't know if they offer you the option of doing either radians or degrees, but it shouldn't be too difficult to switch back and forth. As long as you remember the golden rule, pi is 180. Okay. All right. Now, what about C? 7/6 pi. All right. Well, that's clearly more than pi. Pi, remember, is 180 degrees. So you've gone up into the first quadrant, down to the second quadrant, and then another sixth. Okay. And so in other words, pi over 2 plus pi over 2 plus pi over 6 is 7/6 pi. So that means we've moved pi over 6 degrees, radians rather, into the third quadrant. So therefore the reference angle which on the chart is angle minus pi, 7/6 pi minus pi, which is 1/6, or just pi over 6. So in other words, it is that angle itself. All right, and then finally D, we have 7 pi over 4. All right, so let's see, where would that put us? And again, if you find the radians to be completely confusing, just convert everything into angles, degrees rather. So that way you'll know what the right answer is. And then if you have to convert it back into radians, it will be very simple. So we've got pi over 2. And then we have pi over 2 again, and if you can write this, think of this as pi plus pi over 3 pi over 4 if you want to. So that means when we get to this point, well, actually, that doesn't help us either, does it? No, because each quadrant is pi over 2. So you can think of this as pi over 2 plus pi over 2 plus pi over 2 plus 1 pi over 4. That might be the easiest way to break this up, okay? Because you've got 2 pi over 4 plus 2 pi over 4, 2 pi over 4, pi over 4. So in other words, you basically gone through 3 full quadrants and then a quarter pi over 4 into the 4th quadrant. Okay, and that does in fact add up to 7 pi over 4. So now if you look at the rule for the 4th quadrant, it's 2 pi minus angle. Okay. All right, it's pi over 4. Now remember, what we're looking for is the shortest path back to the horizontal axis. Now I see here, I didn't really draw this as well as I might have. Let me just tidy it up a bit. Because what you're doing is you're going through 3 quadrants and then exactly halfway into the 4th quadrant. So that means this is what you're trying to do. You're trying to return to the horizontal axis, and that will move you another pi over 4 radians. So that's why this is the right answer. All right. Well, now we can get our calculators out and work on these. Now, hopefully you have your calculator, right? I have the GI 84. Now remember, with this calculator, you've got 2 modes, radians and degrees. For the love of God, make sure you're in the right one. All right. Otherwise, all your answers will, of course, be wrong. So your very first step is to switch to radians mode. If it's already there, great. But just double check at least, because you really have no way of knowing unless you go double check. There's nothing on this calculator to indicate which mode you're in, unless you actually look at the mode button. So yeah, mine is already in radian mode. So what I'm going to do is put tangent. Now on this calculator, the pi button is obtained by hitting second, and then you hit the exponentiation key. And then that'll give you pi. Then you divide by 3. Close, enter. So And now it comes back with a decimal equivalent of it's 1.732. Now, the other option you have is to go back to this unit circle. But if you're going to use the unit circle, you have to be careful because it's pi over 3, which is not a problem to find. Oh, in fact, it's just this one. But the thing is, it's asking for the tangent. And we don't have the tangent on the unit circle, do we? No. So you have to remember that you can rewrite this as the sine of pi over 3 over the cosine of pi over 3. And so if you look in the diagram, we'll see that that's going to give us radical 3 over 2 divided by 1/2. And that ratio is the same as radical 3 over 2 times 2 over 1, which means radical 3. So in other words, this is radical 3. So again, with the calculator, you'll get a number where you won't get the ratio of radicals that you would get with the unit circle. And again, I'm not sure if MindTap will accept both of them. If not, at least find out how many digits of accuracy it requires, and then take it from there. Don't lose points because you put it in the wrong form. Now for B, we have the secant of pi over 3. Now remember, the way this works is that the secant is the inverse of the cosine. So if you go to your calculator and ask for the cosine of pi over 3, you'll get, 0.5. Well, that's a nice, easy one. And that leaves us with 2. Okay. Or you could simply go to the unit circle diagram and you'll find it right here. Pi over 3. Yeah, it's the same one. Okay, pi over 3. Great. So you can see the cosine is 1/2, and you'll of course end up with 2. All right. So now for C, we've got the cosecant of pi over 3. Which is 1 over the sine of pi over 3. So you can consult with your calculator, ask for sine of pi over 3. Uh, 0.866 something. And if you invert that, it's about 1.1547. So in a case like this, you may as well double check and see what we've got on the unit circle. This is clearly some radical or other. So again, on the unit circle, pi over 3 is, the sine of pi over 3 is radical 3 over 2. Which in turn means that it's 2 over radical 3. Now, of course, we know that we're not supposed to leave radicals in the denominator, so we will rationalize this. So it's basically 2/3 of radical 3. Okay. And then finally, D, we have cotangent pi over 3. All right, so if we go to your calculator and ask for the tangent of pi over 3, actually, we did this earlier. It was approximately 1.732. And so the inverse of that is roughly equal to um, about 0.5773. And then, of course, if you go to your unit circle, now keep in mind that remember we saw before that the tangent equals sine of the cosine. That being the case, the cotangent must be the cosine of pi over 3 divided by the sine pi over 3. Okay, so that's going to give me from the unit circle. Um, let's see. So the cosine is 1/2 and the sine is radical 3 over 2. So it's 1 over radical 3, but again, we don't want to leave it like that. So we'll rationalize the denominator. So it's about 1/3 of radical. It's exactly 1/3 of radical 3. So that's approximately 0.5773. Right. Now we're going to do the same thing with degrees. Okay. In other words, we're going to use the tangent and all the rest, except with degrees. So again, it's really just a question of knowing the identities because none of these are actually on the unit circle or in their calculator. So for example, the cotangent of 30 is the same as the cosine of 30 over the sine of 30. So once again, we'll go back to our table chart. So 30 degrees is this one now. And so the cosine is radical 3 over 2, and the sine is 1/2. So you see what I've done here? When you divide by a ratio, what you're basically doing is multiplying by the inverse of the denominator. It's the same thing. So this makes it a little simpler to see that this is simply radical 3. All right, now how about cosecant? Now remember the cosecant is the inverse of the sine. And again, you can either go to your calculator or you can go to the unit circle, sine 30. Oh, we actually still have it right here. 1 over 1/2 equals 2. All right. So we're getting pretty good at this trig stuff, aren't we? Well, kind of. No, it's after a while, it's just one of those things that you don't see it too often in most branches of math, especially applied areas, unless you happen to be doing architecture or something. But you still need to know it in calculus, the more advanced calculus courses. So it's good practice. It's all good practice. All right. Now I just realized something's not right here. Hold on. This is every so often it's not reacting. Well, it sort of is and it sort of isn't. There we go. All right. So here we go. Let's try the secant of 30. This is the inverse of the cosine, which is what we already saw earlier, is one over, that means it's 1/radical 3/2, or 2/radical 3. But now we have to rationalize the denominator. And we end up with 2/radical 3/3. Okay. Good. All right. Whatever that happens to be. Cotangent. Now we've already just got through seeing that the cotangent is the inverse of the tangent, which if we're using the unit circle, probably our best bet is to do this. All right, so going back to the unit circle, the cosine of 60 is a half. We'll divide that by radical 3/2. And then that, of course, needs to be rationalized. 1/radical 3 is the same thing as radical 3/3. All right, two more. Oh, and there's a few more. And then that's it. Then we'll be done. Then we can go back to our old friend, matrix algebra. Okay. And you'll be fully prepared, of course, for the second midterm. Now, the cosecant rather, remember, is the inverse of the sine. And we just looked that one up. It was radical 3/2. So this is 1/radical 3/2, or 2/radical 3, which then has to be rationalized. 2 over, oh, sorry. No, wait a minute. What am I doing? You don't want to, the whole point of this is not to do that. 2/radical 3/3. There we go. All right. And then what do we have? Secant. The secant is the inverse of the cosine. So we've already looked up the cosine of 60. It was 1/2. Oh, this one worked out nicely. It's just 2. All right. Now, these last few are a little bit different because there's some algebra going on here based on the identities. So these will be just a touch trickier than what we've been doing, but not much. So, for example, what do we have here? We have the cosecant of, sorry, 30 divided by the sine of 30. But remember, the cosecant is 1 over the sine. So what you've actually got here is equal to, now here's what we can do. Let's rewrite it slightly, just to make sure there's no confusion. Let's rewrite this as, in the denominator, as sine 30 over 1. And so what you've actually got here is 1 over the squared sine of 30. Now, it's often, usually most math books, they write it like this. Okay, that means that it's whatever the sine of 30 is, we're going to square it. So again, if we go back and revisit our unit circle, the sine of 30 is 1/2. Okay. So we've got 1 over 1/2 squared. You can see it's getting a little messy here. So we ultimately end up with 4. Okay. Oh, that was unusual. So you see what I mean? There's that extra algebra in there, but otherwise, what we're doing here is the same as what we were doing earlier. All right, so what about this one? Well, we have the secant over the tangent. Now the secant is 1 over the cosine. The tangent is equal to the sine of the cosine. So here's what we end up with. So these drop out. We actually end up with 1 over the sine of 30. And we just got through showing that the sine of 30 is 1/2. Okay. So therefore we have 2. All right. So, all right. Well, that's interesting. Now, how about this one? Now, for this one, we can look them both up. Sine 30 is 1/2. Cosine is radical 3 over 2. So this is equivalent to saying 1/2 times 2 over radical 3. All right. That's it. We're done. Now, if you wanted to, you could have actually, if you might have recognized that this is also equivalent. Suppose you decided, you know what, I don't want to use the unit circle. Let me use the calculator. You could do it directly, or what you could have done is said, hey, wait a minute, isn't that just the tangent of 30? And you would have been absolutely correct. So you could have gone back to your calculator, making sure you switch back to the degrees mode and typed tan 30, and you would have gotten 0.577 with the understanding that radical 3 over 3, just double check that, is yes, 0.577. Okay. So you've always got multiple options with these trig functions. And then finally with this one, know that the cotangent and the tangent are inverses of each other. So that being the case, we have cosine 30, sine 30 over sine 30 or cosine 30. And again, when you divide by a ratio, it's equivalent of multiplying by its inverse. Which means you've got the squared cosine in the numerator and the squared sine in the denominator. All right. So when we look on our unit circle, cosine of 30 is radical 3 over 2. And the sine is 1/2. You got 3 over 4 divided by 1 over 4. And you ultimately end up with 3. So we're done with this. So there's nothing left on the second midterm that you might encounter that's not here. All right, so like I said, I'll post this because it's got all the nice hand drawings in it, but I'll also post the formal written out solutions that like I always do, onto Brightspace as soon as we're done here, and that way you can study from either one of them or both. And now we can move our attention back to matrix algebra, which we haven't thought about in a while, but we'll just go back here and revisit it. And just a quick reminder, a matrix is simply an object which has rows and columns, and it's usually used to represent a system of simultaneous equations. So what we did not quite get around to yet was matrix multiplication. We define matrices. We define their dimensions, and we saw how to add them together. We saw how to multiply them by a scalar. Okay, so this is a quick review of that. Um, we make a couple of quick examples here. A matrix has dimensions equal to its rows um, times its product, but its columns. Just rows times columns. In other words, if you have a matrix like this, let's say this is matrix A, it is of dimensions 2 by 3 because we have 2 rows and 3 columns. Okay, and then we might have, let's say, B. In this case, we have dimensions 3 by 2 because we have 3 rows and 2 columns. Sometimes we have a matrix which has the same number of rows and columns. Let's say this is matrix C. And so when the rows equals the columns, matrix is said to be square. All right. Now we'll see why that's so important later on. It turns out there are certain matrix operations that can only be performed on square matrices. Okay. Now sometimes we may have a case where we only have a single row or a column. And we often refer to this as a row vector. Sometimes a row, a matrix. A vector is simply a special type of matrix where there's either one row or one column. So you may hear both of those terms in the book. So this is a column vector or column matrix. Okay. And then there's another case that you might run into where you have just a single element, one by one. It's just a number. It's a single number. Okay. It has the same properties as a simple real number. So we call this a scalar. And then we saw how to add and subtract matrices. So let's say this is matrix A and B. Important detail here is this is not going to work unless if they have the same dimensions. Addition takes place on an element by element basis. All right, so in other words, in the most general terms, let's say we have this case. Now, remember, we use this notation to indicate the elements of a matrix. You can tell where it belongs by the subscripts, okay? So Aij is an element of matrix A with row I and column J. Okay, and then you can do the same thing for B. And if you notice, well, we'll identify this one too, of course. It's an element of matrix B with row I and column J. So can I add them together? Well, yes, because since both matrices have the same dimensions, they can be added together as follows. So we have a new matrix, A plus B, which would be written in the following way. It has the same dimensions and all we did was add them together. Okay, element by element, like I said. So let's go back and grab that example we had a minute ago. And yes, I want to point out here that this is 2 by 2 because each of the individual matrices had dimensions 2 by 2. Okay, so the example I started out with is up here. Now this is kind of nice. I can't copy and paste in the board. This is very helpful. So we're going to end up with a new 2 by 2 matrix. The first element is 1 by plus 5. Okay, and we have 2 plus 6, 3 plus 7, and finally 4 plus 8. All right, so then we obviously add them together, and our final result is all right. And the same thing would be true with subtraction. You would just go through and subtract the elements one by one. So addition and subtraction are the same thing. We have to have the same number of dimensions, otherwise we can't do this. We also looked quickly at scalar multiplication, which is especially simple. With scalar multiplication, each element of a matrix of any dimension is multiplied by the scalar. So there's something like this. Right? So keep in mind that with this operation, the dimensions of A are not relevant. We can, no matter what they are, we can always multiply it by a scalar. Okay, there's no restrictions on this. Okay, so we know that A is 2 by 2. And so we're going to go ahead and do this. Now, it's exactly like you would think. We're literally going to multiply every element of A by 3. Okay. Actually, I have one for it right here, I think. Well, maybe not. Let's do it here. So you can see I just went through and literally multiplied every element of A by 3. Okay, that's all there is to it. And of course, the dimensions of the new matrix are the same as A. Okay, so that leaves us with 3, 6, 9, 12. And it's that simple. So now those are the easiest cases. The next one is the challenging one. We're going to now multiply two matrices together. Not a scalar, although scalar is technically a matrix. It's a special case. For all other cases, we have to follow certain rules. And also, matrix multiplication has restrictions on it, which has to do with their dimensions. Okay. Now, I don't remember if we started this or not. I don't think so. But it's possible I briefly mentioned it. Let's jump ahead here. All right. So here's what we have to do. Imagine we want to multiply two matrices together. We have matrix A, and let's say its dimensions are n times p. And we have matrix B, dimensions are p by m. So the way it works here is this. Two matrices can be multiplied together if the number of columns in the first matrix equals the number of rows in the second matrix. So in other words, using a diagram, which I think is the easiest way to visualize it, these have to be the same. All right. If not, then matrix multiplication is undefined. Now, if we are allowed to do this, now in formal language, there's always formal language in math. In this case, so matrices are said to be conformable multiplication. All right, that's the official terminology there, conformable. I don't think they expect you to memorize this for MindTap, but anyway, if the matrices are conformable for multiplication, then the resulting matrix will have dimensions or will have the same number of rows as the first matrix and the same number of columns as the second matrix. In other words, in this case, n by m. So I'll just sketch this in here as well. AB will have dimensions n by m. All right, now that all sounds very abstract, but once you've done a few of them, you'll say, oh, come on, what's the big deal? All right, so let's start with a very simple case. Let's just do two square matrices, 2 by 2s. Okay. We don't want to get overwhelmed with the details right up front. Here's A, here's B. They're both 2 by 2. And you can see they are conformable for multiplication. Okay. Otherwise, we'd have to stop what we're doing. And then A times B will have dimensions 2 by 2. Okay. So how exactly does one go about this? All right. So why don't we start with a general example? Let me just show you how this would work with these with this notation. So this is A, this is B. This is 2 by 2, 2 by 2. The resulting matrix we'll call it AB, and we'll have dimensions 2 by 2. So That being the case, um, why don't we think of this as AB11, AB12? No, actually, yeah, that's fine. That's fine. All right. So where do these numbers come from? All right. Well, here's what we have to do. We're going to multiply, not in a way you might expect. Okay. So I'll tell you what, let's use the actual numbers for the first example. It'd probably be easier to follow along. All right, here we go. So there's A and B. So in the upper left-hand corner, we're going to multiply, since this is element AB11, that means we're using the first row in the first column. We multiply the elements in the first row of A by the first column of B. In other words, you're multiplying 1 times 1 plus 2 times 0. Okay. So I can see already I'm going to run out of space. So I'm going to rewrite it slightly. Yeah, I'm gonna put the this notation down here. All right, so this is what I was calling AB11. Now, what about AB12? We're going to take the first row and multiply it now by the second column in matrix B. All right, so this time we're going to have the same row, but over here, column 2. So meaning we're going to have 1 times 2 plus 2 times 1. Okay, so it's the first row, the first matrix times this time the second column. And you can tell because of the indices. Now, down in the bottom left-hand corner, this is the element AB21. We're going to use the second row up here and the first row, the first column rather, over here. So that means we have 3 times 1 plus 4 times 0. And then finally, in the bottom right-hand corner, we're going to be multiplying the row 2 by column 2. Or, in other words, 3 times 2 plus 4 times 1. So really, all of this, the hard part is lining it up correctly, making sure you're multiplying the right row by the right column. The rest is easy. It's just straight ahead algebra. So in other words, when you multiply these out, you're going to end up all together with up here I have 1 plus 2, 0, which is 1. On the right, we have 2 plus 2, which is 4. The bottom left-hand corner, we have 3 plus 4. In the bottom right-hand corner, we have 6 plus 4, which is 10. Oh my God, what an ordeal that was. But I'll tell you what, after you've done about 5 or 6 of these, you'll say, where's the hard ones, please? Okay, so in other words, it's just a question of getting used to it. So I'll tell you what we should do here. I think we should make up another one and do it again from start to finish. I'll pick the same dimensions, by the way. We won't change dimensions until we're really comfortable with this. All right, so you've noticed this one is 2 by 2. And so that means they are conformable. The new matrix AB will be 2 by 2. So the first element, which I'm calling AB11, will be the result of multiplying row 1 times column 1, meaning this row by this column. That means we're going to have -1 times 2 plus 0, 0 times 0. All right. Then over here, we'll have row 1 times column 2. Same row over here, -1. Now this times the second column. -1 times 1 plus 0 times 3. Great. Now down here, the element which we're calling AB21 is going to be row 2 by column 1. Okay. Row 2 is multiplied by this first column. We'll have 2 times 2 plus 1 times 0. And then finally, this last element is row 2 times column 2, meaning 2 times 1 plus 1 times 3. So, of course, now we do all the calculations. In the upper left-hand corner, we have -2 plus 0. Upper right-hand corner, -1 plus 0. Bottom left-hand corner, 4 plus 0. Bottom right-hand corner, 2 plus 3. And that's our final result. And if you notice, the dimensions are 2 by 2 because the first matrix has 2 rows, the second has 2 columns. Oh my God, yes. All right, so I'll tell you what, let's do another one. I'll continue to use, by the way, 2 by 2. Later on, we'll change that to something else when, you're more comfortable with this. Okay, so once again, we know that these are compatible or conformable with each other. Otherwise, you'd have to stop. Okay, and the resulting dimensions will be 2 by 2, 2 by 2. But what are they? All right, let's see. So we'll start up here. Row 1, column 1 is 1 times 0 plus 2 times 3. Over here, we have AB12, which is row 1 times column 2. And of course, this is column 2. And so we're going to have 1 times 1 plus 2 times 2. Great. Now we're going to adhere to the bottom. Row 2 times column 1, we have -2 times 0 plus 3 times 3. Then finally down here in the bottom left-hand corner, second row, second column will give us -2 times 1 plus 3 times 2. Right? So notice these two and then these two. Now we just have to do the actual calculations. Upper left-hand corner is 6. Upper right-hand corner is 5. Bottom left-hand corner is 9. Bottom right-hand corner is 4. All right, now I'm going to let you in on a little secret here. If you are a friend of Microsoft Excel, you use it or you're willing to use it. What if I wanted to confirm this? I'm like, I don't know what I'm doing here. I just want to make sure that this looks right. I'll type in the elements. Now, just to make it more, let's say, visible what you're doing, I'm going to highlight the cells from the two matrices. And this is my resulting matrix. I guess let's make this another color, orange. If I really am not sure what the result will be, here's what you do. You select the entire set of cells. This is, by the way, this is A, this is B. Hold on. Okay, select all of this. Now, again, if you're not comfortable with Excel, you may not, be familiar with how its commands work, but this is something you may, even if you're a good Excel user, you may not have run into this before. If you type equals M mult for matrix multiplication, you're going to put in for the first value, matrix A, which is in cells A1 through B2, comma, same thing for B. Now, don't hit the enter button, which is what you normally do. You have to hit 3 buttons. I'll make a note of it over here. Hit Shift, and this is for PC, by the way. Hit Shift, Control, Enter all at the same time, like a piano chord, all at once. And you'll see it fills in all 4 cells. And guess what? It matches what we did. How do you like that? So that way, if you're doing one of these problems, you can double check the results in Excel if you want to. Uh, See, now I've given you a lot of helpful hints there. Um, it's very simple if you know what you're doing, if you or knew that this was in here. But if you didn't, well, I have a feeling that Symbolab can do this too. I just don't know how it operates with matrix algebra. Maybe later on we'll investigate that. But there's one way you can double check your results, because this is, after all, a very messy process, let's face it. So we're going to have to practice with this quite a bit. This is the one thing that's really going to take a while to get comfortable with it. But again, it's really all about keeping an eye on those dimensions and making sure you're lining them up, that you're using the right row, the right column. And so you're really more organizing it than anything else. Now, I don't want to push my luck, but I'd like to try a case where they do not have the same dimensions. All right, so how about this one? A is 2 by 3, B is 3 by 2. These are conformable for multiplication. The resulting matrix AB two by two. So it's going to take a little bit longer because there's more elements, but you'll see that it's exactly the same logic. All right. So we have A, B1, row one times column one. That hasn't changed. What's changed is the number of elements. So in other words, here's row one, here's column one. So this one will be 1 times 1 plus 2 times 2. And then 3 by 3 times 3. Okay. No, of course, we'll just add them up. Then over here, we'll do row 2. Row 1, column 2. And that's going to give me the same row, but this column, 1 times 0, 2 times 1, and okay, I see I didn't leave enough room here. Hold on a second. All right, that's better. Okay, here we go. 3 by 2, or 3 times 2. Right. So here we're going to have row 2, column 1. So this is row 2, of course. 4 by 1 plus 5 times 2, 6 times 3. And then the very last element, AB22, will be the second row times the second column. Oops. Meaning 4 by times 0, 5 times 1, 6 times 2. So we just barely fit it in there, but we got it in there, and just barely, but we got it. So the final result would be 1 plus 4 and 9, 4, that's 14. Over here in the upper right hand corner, we have 0 plus 2 plus 6. Down here we have 4 plus 10 plus 18. Okay, 32. And then in the bottom right hand corner, we have 0 plus 5 plus 12, 17. And you notice it is in fact 2 by 2, as we predicted. So why don't we go to our new best friend, Excel, and confirm this. We have for A, 1, 2, 3, 4, 5, 6. And over here, we have 1, 2, 3, 0, 1, 2. All right, so I'd like to keep doing the same color scheme, so again, it's easy to see what you're doing. And now, of course, we already know that the product of these two will be 2 by 2. So let's store that over here. And so here's A, 3 by 2, B, 2 by 3. Sorry, no, my mistake. This is 2 by 3, 2 rows, 3 columns. This is 3 by 2. And so AB will be 2 by 2. I didn't write them here. I'll do that right now. All right, so let me show you once again how this works. The command is called M. Now, first you have to select all 4 cells. Otherwise, you'll only see one of the cells. So mmult. And all you have to do here is just tell it where to find the cells in A and in B. And then don't forget Shift. Oh, that's a different one. Shift Control Enter. And so did we do it right? 14, 8, 32, 17. Yes, it is correct. All right, so let me sneak this in here. Select all the cells in the matrix. Enter. Shift, Control, Enter. And that'll do it. Wow. How do you like that? So anyway, like I was saying, this is probably the trickiest operation we'll need to perform. Well, we'll see about that. So there's some here that we haven't actually done. I think, when we get back on Monday, I think we'll take a look at these because now I think you're starting to get a feel. See here, what they've got is 3 by 2 times 2 by 2. So we end up with a 3 by 2. So, the more of these we can do, the better. Then that enables them to introduce some more key properties. Now, by the way, I do want to mention here that this is one of the quirky things about matrix algebra. Because of their dimensions, you notice how AB works out just fine. But if A has dimensions 3 by 2 and B 2 by 3, AB is conformable for multiplication. But now this is a key detail. What about B times A? Oh, well, that worked out rather well. Usually we don't get so lucky. Yeah, this is one of those cases where it actually did work out. But often when we flip the two, they're not conformable. I just realized this is probably not the best choice, but most of the time, and so oh, wait a minute. No, no wonder it didn't. I think I just wrote the wrong numbers. No wonder. All right, hold on. If that was the case, then it would have worked. But unfortunately, I just realized I goofed it up. It was 2 by 3, and this one was 3 by 2. That's why, yeah, okay. So it didn't turn out the way I wanted it to. So unfortunately, I've messed this thing up. It should have been 3 by 2. Now you notice it still is conformable, but this time the result um, let me just make a note here. It has dimensions 2 by 2. Um, but this time, the resulting dimensions of B would be 3 by 3. Okay. So that would be an important difference. So the two matrices, not only you're not going to get the same answers, but you're not even going to get the same dimensions. Now, let's try a different scenario. Let's say A is 2 by 4 and B is 4 by 3. Then these are conformable. Or actually, I shouldn't write it like that. It should say A and B are conformable. That would be more proper English. Here, A and B AB would have dimensions 2 by 3. Now, this is what I wanted to illustrate earlier, and like I said, I didn't really pick the best choice. B times A is going to be a problem though, because, oh no. Actually, I'll tell it. Let me write it like this so it's clear that we're multiplying B times A, not the other way around. B and A, in this case, are not conformable. So, in other words, AB does not exist, or BA rather does not exist. Okay, it's because they don't match. The dimensions don't match. So that one would just simply be undefined. Now, you know what we could do in Excel real fast? Let's try it just for the fun of it. See what happens if I reverse these two. We know that these two are conformable in both directions. Um, according to this, I'm going to end up with a result of 3 by 3. Just trying to get this thing out. So I need to select 9 cells. So this one has dimensions 3 by 3. So if I multiply them together, equals M mult. So I come here and choose a B rather, and then A, hit Shift Control Enter. You can see this is what it looks like now. So that's BA, this is AB, and they're very, very different, aren't they? Yes, they are. So this is one of the weird things about matrix algebra you don't run into with the real numbers. In other words, 3 times 7 is the same as 7 times 3, any way you look at it. But here, it's not the case that A times B is the same as B times A. So in matrix algebra, we say that um, matrices do not have a commutative property for multiplication. Okay. Now, it's not a problem for addition because we require the dimensions to be exactly the same. But here, um, we see that either A and B and B and A are either different or else one of them is not even defined. All right. So I think that was it might have been a bit overwhelming. We'll do some more practice with this when we get back on Monday. But this chapter, the MindTap assignments for this chapter aren't due for a while anyway, so we'll have plenty of time to practice with this. What comes after this is something called the inverse, which essentially takes the place of division in matrix algebra. This is the equivalent of division in matrix algebra, and this one also is a bit intense. But well, we'll work on that. Okay. And then we're going to tie together and see how we can use all of this to solve for systems of simultaneous equations, which is really what this is all about ultimately. It's fun for its own sake, but let's face it, what we're really after is solutions. Okay, so we'll cut it off right here, and I'll be posting all this good stuff that we've been working on today, and including the recording, of course. And then when we get back on Monday, we'll just pick it up where we left off right here. Okay, so I'll see you all then.
Bye. Thank you.
All right, bye. See you later. Thank you. Okay, you're welcome. Okay, you too.